So this is the page that was missing because I was collating and I got the wrong page in. So we're given the shorthand notation and we're asked for the E of the cell and the cell reaction. So we would just take our shorthand notation and write it out. So this would be 2 aluminum solid goes to 2 aluminum plus 3 plus 6 electrons, and you have to look up the volts in your table in your book. So 1.66 volts. Then we have 3 iron plus 2 plus 6 electrons, go to 3 iron solid, and it'd be a minus 4.44 volts. What I like about this is you just have to add up the volts. And then you add up the left-hand side and the right-hand side, and that gives you your cell reaction right here. So in the next question, we are given a system with aqueous iron and aqueous potassium permanganate, manganese iron, solid iron, and we're supposed to predict the spontaneous galvanic cell and cell reaction. So we're going to put the manganese as gaining electrons because we can have a positive 1.51. We'll multiply by 2 because we have to have 10 electrons for each of them. So this is going to be gaining electrons. Then we're going to put the iron as losing electrons. We're going to multiply it by 5 so that we have 10 electrons lost. And then it's going to be a plus 0.44 volts. All we have to do now is add up our volts and add up our reactions. So this is going to be your overall reaction. Okay, so now we're going to look at equilibrium constants from EMFs. So we're going to relate the free energy to work. So free energy equals work maximum. Work maximum equals minus, work maximum equals minus FE of cell. And therefore, the free energy at the standard state is minus NFE of cell. So here's our example. So using the standard electrode potentials, calculate the standard free energy change at 25 degrees C and the equilibrium constant for the reaction. And then here's your hint of what you're going to need to use. The delta G at the standard state is minus RT natural log of K. So here's our reaction. We're going to break it up into the half reactions. So the zinc goes to zinc plus 2 electrons at a 0.76 volts. Then the silver ion plus 2 electrons goes to silver solid. It's a 0.80 volts. So we add up the volts, we add up the reactions, we get this for our overall zinc solid plus 2 silver ion goes to zinc ion plus 2 silver and a 1.56 volts. Then we're going to use the equation delta G in the standard state equals minus NFE of cell in the standard state. So our N is 2. This is our Faraday's constant. And then we take the E of cell and put it in here. Then we're going to use another equation. Delta G over minus RT equals natural log of K. So we're going to take our delta G and put it in here that we got from the previous. This is our constant for R. This is our temperature. That equals natural log of K. We take the antilog of both sides. And so we get the equilibrium constant. Okay, so that was the missing page. So then we already did this, and we're going to go on to our new material. Okay, so here's our new material, electrolytic cells. So electrolysis, the process of producing a chemical change by using an electric current. Electrolysis of molten sodium chloride is how it's produced commercially. So you would have sodium ion that's liquid, plus an electron would go to sodium atom that's liquid. Chloride ion that's liquid would go to 1/2 of a chloride that's gas plus an electron. We add up and cancel the electrons. So overall, it's sodium ion liquid plus chloride ion liquid would form sodium atom liquid plus 1/2 of chlorine gas. So lithium, magnesium, and calcium metals are all obtained by the electrolysis of the chlorides. So this question is asking you to write the half reactions for the electrolysis of the molten compounds. So this is the compound, so it would be potassium ion liquid plus 1 electron goes to potassium atom liquid. And then 2 chloride ions liquid would go to chlorine molecule gas plus 2 electrons. This is not asking us to balance, so we'll just leave like this. Then potassium hydroxide, you'd have potassium ion liquid plus an electron goes to potassium atom liquid. And then we'd have 4 hydroxides liquid going to oxygen gas plus 2 water gas plus 4 electrons. So let's look at the electroplating of metals. So if we have zinc ion plus 2 electrons, we can make zinc solid. So what do you expect to be the half reactions in electrolysis of aqueous copper 2 sulfate? So in species and present in solution would be copper ion, sulfate ion, and water. So our possible cathode reactions would be copper ion solution, plus 2 electrons, goes to copper solid with a 0.34 volts. Or water liquid plus 2 electrons goes to hydrogen gas plus 2 hydroxide, that's a minus 0.83 volts. So 0.34 volts is greater than minus 0.83 volts. So that means we pick this one. The possible anode half reactions, 2 sulfate going to S2O8 minus 2 plus 2 electrons with a minus 2.01 volts. Or 2 water liquid goes to oxygen gas plus 4H plus 4 electrons, that's a minus 1.23 volts. We're going to pick this one because this number is larger than this one. We need to make the electrons the same, which is why we multiply this by 2. And then we get our overall reaction, that this is the half reaction for the copper, and this is the half reaction for the water. So there's our, oops. Nope. So there's our overall. So now we're going to do some stoichiometry. So the quantity of a substance liberated at an electrode is directly proportional to the quantity of electric charge that has flowed in the circuit. For a given quantity of electric charge, the amount of any metal that is deposited is proportional to its equivalent weight, which is the atomic weight divided by the charge on the metal ion. So we're going to look at some terminology. Electric charge depends on the current in the circuit and the length of time that it has been flowing. So our equation is electric charge equals electric current times time. The units of electric charge are coulombs. The unit of electric current is ampere. And typically we use time as seconds. So note it is fair game to ask questions involving dimensional analysis using Faraday's constant. Okay, so we're going to do some examples. So we have a constant current. It's passed through copper sulfate, 5 hours, 404 milligrams of copper is deposited. What must have been the current? So we're going to start by writing the half reaction. Copper ion plus 2 electrons goes to copper solid. And now we get to do a series of conversion factors. So this is all about the units. Okay, so if we look at the units, we have a lot of numbers in the problem, but we want to get the units to cancel. So we're going to start with 0.404 grams of copper and the atomic mass, 63.6 grams of copper to 1 mole of copper. For 1 mole of copper, we have 2 moles of electrons. We get that from here. 1 mole of electrons is the Faraday's constant. That's here. It's in coulombs. 1 coulomb is an amp second. So we're going to have to divide by our 18,000 seconds to get rid of those seconds. So we end up with amps. So this is your answer in amps. So you will get to use your dimension analysis skills on these problems. So this is asking when aqueous potassium iodide is electrolyzed using platinum electrodes, diatomic iodine is produced. How many grams of iodine are produced when a current of 8.52 milliamps flows through the cell for 10 minutes? So here's our half reaction. 2 iodide goes to iodine plus 2 electrons. So we're going to take our 8.52 times 10 to the minus 3 amps, multiply that by the time in minutes, convert our minutes to seconds so that we can get coulombs. Then we're going to take the coulombs and use the Faraday's constant to convert to 1 mole. There's 2 moles of electrons per 1 mole of iodine, which we got from this half reaction. And then 1 mole of iodine is 254 grams of iodine, and so then we get our answer. Okay, so the next question is asking us about the electrolysis of water. So this is one of the possible half reactions for the electrolysis of water. So water liquid goes to oxygen gas plus 4H plus 4 electrons. And our question, if 0.076 liters of oxygen at 25 degrees C and 755 millimeters of mercury is collected, how many coulombs of electricity had to pass through the solution? You're going to have to use PV equals nRT. So here's our pressure. We need to convert that to atmosphere. The volume is going to be in liters. We're solving for N. We use the ideal gas law constant. And then our temperature is in Kelvin. So when we use the PV equals nRT, we get our N, 3.0859 times 10 to the minus 3. So we're going to take those moles and then convert the moles of oxygen to moles of electrons, because we have that 4 up here. So 1 oxygen is 4 electrons. And then 1 mole of electron is 96,486 coulombs, Faraday's constant. And so here's your final answer. Okay, so this is a little diagram to practice a simple Daniell cell. And there's a lot of possibilities, but we're going to just look at zinc going to zinc plus 2 is a 0.76 volts. And chloride going to chlorine gas is a minus 1.36 volts. We're going to use those. So if we use those, our system would look like this. Here's our piece of zinc. We would have zinc nitrate. We'd have to bubble chlorine gas into the solution, and we'd have to use graphite as a conduit for the electrons. So the question's asking what constitutes an electric current in a wire, and that's the electrons moving. Indicate the direction of these particles by drawing an arrow over each wire. So we're going to see this when I show you the half reactions. The arrow goes here. The zinc is losing electrons, and the chlorine gas is going to be gaining electrons. So that's what it, when it says to indicate the direction of these particles, that's what it means here, the electrons. They're not particles, but what constitutes an electric current in a solution? You've got to have some ions present in the solution so that you can have an electric current. Then why must there be actual contact of the two solutions? Oh yeah, so we're going to have a salt bridge to prevent a concentration gradient. And we need to have the salt bridge so that we don't have the concentration gradient. Because in other words, if the zinc keeps going to zinc plus 2, after a while it's not going to want to do that. Okay, so here's how we know the half reactions. The zinc is going to go to zinc plus 2 electrons, and that was a 0.76 volts. You have to look that up. The chlorine gas plus 2 electrons goes to 2 chlorides. That's a 1.36 volts. You have to look that up. So we know that this is losing electrons, and this is gaining electrons. So that's how we can do the electron flow. The total cell reaction is just add them up. So zinc solid plus chlorine gas going to zinc plus 2 plus chloride. We add up the volts and we get the experimental voltage for the cell. Okay, so this is a worksheet that you were supposed to do that should be in your handout. And we're showing the flow of electrons here. And then I'm showing that we're losing aluminum and we're gaining the lead. And that's because of the half reactions. So we're going to answer the questions. Number 1, which is more easily oxidized, metal, aluminum, or lead? That would be aluminum. What is the balanced equation? So it's 2 aluminum plus 3 lead goes to 2 aluminum plus 3 lead. You have to do the half reactions in order to determine this. Lost. So the maximum voltage is the 1.353. And I got that from down here. The direction of the electron flow in the wire is aluminum to lead. So aluminum is giving off electrons. Lead is gaining electrons. So it all goes back to the half reactions to be able to answer these questions. The direction of positive flow in the salt bridge is aluminum +3 to lead +2. Which electrode is decreasing in size? Aluminum. Aluminum is getting smaller. It's becoming an ion. Which electrode is increasing in size? Lead. Lead's going from the ion to deposit lead solid. What is happening to the concentration of aluminum ions? They're increasing. What is happening to the concentration of lead ions? They're decreasing. What is the voltage in the cell when the reaction really reaches equilibrium? 0. So the anode is the aluminum going to aluminum +3 +3 electrons. And the cathode is a lead ion +2 electrons going to lead solid. So the positive electrode is the lead. The negative electrode is the aluminum. Okay, so this crossword puzzle was just so that you could have some fun. So I'll let you fill that in. Then here's the rest of it. And then this is so that I can have some fun. Okay, this is not in your notes. You're going to want to add it. You're going to make yourself a little table. So this is the alkane. These are examples of alkanes, and I've given you the formula. So the name is methane. Its formula is CH4. Ethane is C2H6. Propane is C3H8. Butane is C4H10. Pentane is C5H12. Hexane is C6H14. Heptane is C7H16. Octane is C8H18. Nonane is C9H20. Decane is C10H22. Undecane is C11H24. And dodecane is C12H26. So my suggestion to you is not to memorize the equations, but to memorize the sequence. So example, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, undecane, dodecane. And then you can use your fingers. So starting with 1 is methane. So you're going to have to learn a new language when you take organic chemistry. So we're going to look at that just a little bit. So the prefix will tell you how many carbons, which is why if you've memorized the sequence, then you'll know meth is 1, eth is 2, prop is 3. The suffix tells you about the bonding. So if you have single bonds, it's an ANE. at least one double bond, it's an ENE, and at least one triple bond, it's an INE. So ein, ene, ein. So then there's alkyl groups, which means you took the alkane. So in this example, the alkane is CH4, and you took away a hydrogen. So CH3 is a methyl group. CH3 is ethane, but we take away one of the hydrogens, and we have CH2, CH3, and now we have an ethyl group. So for the numbering, you either go from right to left or left to right, whichever gives you the lowest number. So this is an example of giving us the lowest number. We're going to start with 1, 2, 3, 4, so that the first carbon has the double bond, rather than the other way around. You're going to have to go both ways and then just figure out which has got the lowest number. So then we have some problems to practice, and I believe you should have these in your handout. Okay, so if you notice this one, it's 1, 2, 3 going across. This one is 1, 2, 3, 4, but we have a double bond on carbon 1. This one is 1, 2, 3. We have a triple bond on carbon 1. This one is 1, 2, 3, 4, 5. So 1, 2, we have a methane on carbon 2. Okay, you're going to want to be careful here. It's the longest continuous chain. So this is our longest continuous chain. No one's going to write it all nice and neat and horizontal for you. You have to be able to go upside down, backwards, whatever you need. So here's our longest continuous chain with the methyl group. Here's our longest continuous chain with on carbon 2 double bond. And then here's our longest continuous chain with the ethyl and the ethyl. So what you're going to find is that organic chemists do not feel like drawing the H's, and trust me, when you get to 25, whatever H's, you will not want to draw them. So what you have to get used to is that you draw the carbons, you draw the bonds to the H's, and you just have to know that the H's are there. And you can name it because you go by the name of the carbon. So 1, 2, 3, prop, single bonds, ane. So this is propane. So this next one, I've got 1, 2, 3, 4, which is my bute. On carbon 1, I have a double bond that gives me the ene. So this is 1-butene. Okay, this next one's got 1, 2, 3. That was prop. On carbon 1, there is a triple bond. That's the ine, so 1-propyne. This one does simplify to just propyne, because if it was on this carbon, that'd be carbon 1. If the double bond was between this carbon and this carbon, it'd still be carbon number 1. You're going to want to make sure to ask your professor, are they going to be okay with you doing this? Because some professors will take off if you put that 1, but I don't. But this is the proper name, and it does simplify because whichever way you go, the triple bond is going to be on carbon 1. Okay, this is what I was saying about being able to go backwards or upside down. So 1, 2, 3, 4, 5. That would give us our methyl group on carbon 2. If we did 1, 2, 3, 4, that 4 is bigger than 2. So we're going to go this way. 1, 2. There's our methyl group. And then 1, 2, 3, 4, 5. That's our pent. All single bonds, so ane. So 2-methylpentane. This is all one word. I know it looks a little spaced out, but one word. So this has got 1, 2, 3, 4. See how I straightened it out for myself to make it easier? And then it's butane. Okay, here's our longest chain, 1, 2, 3. There's a methyl group on carbon 2, so 2-methylpropane. Okay, this one, 1, 2 with the double bond. So 1, 2, 3, 4, 5, that's our pent. Double bonds on carbon 2, that's our ene. So 2-pentene. Okay, so this one, our longest chain is 1, 2, 3, 4, 5. That's our pentane. This is the ethyl group. This is the ethyl group. That's our diethyl. They're both on carbon 3. Each of the ethyl groups needs a number. That's why it's 3, 3 diethylpentane. Okay, so this was just for fun. It's not going to be on your exam. It's not going to be on the final, but I just thought it would be fun.